I should tell you this or not, but somebody wrote the test today, and they said it was easy. So I flipped through their answers, and I saw a couple mistakes, but mostly it was good. All right, so we're going to do another example of converting. We're going to start with loop invariance and code and convert it into a machine. All right? And before we do that, remember we did this compiling compiling thing, and I realized that we could make it a little bit more tricky. All right? So here, what are we trying to do? We're trying to understand how this meta language works, right? You need to be producing this meta language, and so to help you understand how it works, we're going to talk about a compiler that compiles it into a true Turing machine. And what are we changing from what we did last class is here ooh, sorry about that. Here, so what we're doing is it's taking the value of C and adding it to Y in this example, right? And what are we writing? We're writing the sum. We're given it. We have a current value of X and Y, and we're outputting the sum, right? So now we're going to rewrite the compiler to handle that case, right? Everybody good? So how does the compiler go? Again, we loop over all values of X and Y and C like we did before. And again, we say what is our start, what is the state that we're in, right? We form it. Did everybody follow that? Right? And now, remember, what I keep saying is people say, how does the Turing machine do this math? Right? And the answer I give is what? Table lookup. Right? So somebody has to do the math in order to put it in the table, right? And who does that? That's what we're going to do right now, right? Right now we're going to do the math and put the answers in the table. All right, so you ready for it? All right, here we're going to calculate. Oh, what do I need? I need a value y prime plus c. That's going to be y prime plus c is going to be my y double prime, right? It's a value. I know, right, at this moment, I know what y prime is and I know what c is because I'm looping over them, right? And I'm making the times table, right? In some ways, there's not times here, it's plus, right? But if you were making a times table, you'd loop over all x and all y and you'd store x times y, right? So that's what we're going to do here. We calculate these things that we need. And then, right, that's what here we're doing the math that the table lookup has the answers, and then we calculate the new state, right? And the new value of y is going to be this y double prime, right? And that's the name of the state. And what do we write? Here what value do we, if for this table entry, what value gets written by the Turing machine, by the table entry, is the C prime. Right? Is that making sense? Right? So this is still straightforward. Everybody got that? All right. So we're going to get out of that, and we're going to start again with compile time versus runtime. All right? I think we've done these slides already, but at some point I thought you needed them earlier. So I copied them from here and put them way, way, way early. But let's do them again, just so we know. Right? In fact, this is going to be practice for your test, right? Because your test, you're going to have to do some first-order logic things just like this. Right? And this is, in fact, it's this kind of thing why I subject you to so much first-order logic, right? You have to say, can I multiply two integers in one time step? Can you? You could say, yes, we just did it. Remember, we just did it. Did we multiply two integers? We were actually adding them, but we could have been multiplying them. Did we add two integers? Did we add two arbitrary integers? Bounded. Bounded. Right? Don't forget those two things. Right? No. You can't even remember an arbitrary integer. You only can remember a bounded integer. My finite state automata, my Pooh Bear's blackboard is finite in length. Right? It's fixed size. I fixed it. And Pooh Bear can do any calculation of what he knows. But if he doesn't know it, he doesn't know it. Right? So Pooh Bear only knows x's that are in this and y's that are in this range. And if he knows those, he can do whatever he can do any calculation of those. Right? So here what we're saying, is this true? What does this mean? Everybody needs to know, understand this. Right? If you don't understand this, you're going to bomb the test. Right? This is exactly the kind of thing on the test. Right? It says, can I multiply? Right? Well, what can I do? For every k, I can multiply as long as my numbers are bounded by k. Right? I might need k squared states. Right? I need to remember the x. There are k values for x. I needed to remember the y. There are k values for y. And then we do table lookup. And we know the answer. Right? So for every k, there's a Turing machine that has k squared states. And it can multiply numbers that are bounded by k. Is everybody getting that? Right? And if I were to ask you to prove this using the game, right, we would, how's the game go? Oh, I guess I don't play the game. How do we play the game? We say what? Let k be an arbitrary integer. Let m, now do we have to go into really lots of detail when I give you this much space? No. But the more detail you can give me, the happier the marker would be. So if I was going to do it, I would say, let m be a Turing machine that has m squared states, and that with table lookup can multiply, right? With bounded numbers. And then I say, let x and y be arbitrary numbers that are bounded. And then I can say, well, by table lookup, I can do it just fine. Right? Everybody got that? That's what you need on the test. All right? If you understand that, you're going to be fine. If you don't understand that, you won't be fine. Right? Everybody understand that? All right. So here's another one. Can you multiply arbitrarily in one step? No. Right? No, you can't remember arbitrary numbers. The number of states needs to grow as a function of x and y, right? So how would I prove that you can't do this? Everybody listen to this. Let's write this on the board. What's the negation of this? Negation is that for all Turing machines M, there exists an x and a y such that the Turing machine on x and y doesn't multiply. Right? So how would I write that? This is a for all. So what do I do for alls? Let M be an arbitrary Turing machine. Right? Let K be the number of states. In fact, I'm going to cheat a little bit. Let's say k squared is the number of states, right? So then I'm going to say it can't have a k by k table. Right? It only has k squared states. It can't be remembering k squared answers. Right? You're giving me an arbitrary Turing machine. It could have billions and billions and billions and billions of states. I don't know, but it's bounded. So there's some k, which is the square root of the number of states it has. Right? So it only has k squared states. In fact, let's be it k squared minus 1. Let k squared minus 1 be the number of states. Right? Now, it can't remember k squared answers. So there's some xy pair that it doesn't know the answer for. Right? So now it exists. So I have to say let xy be the pair that M does not have table lookup. Right? So if it doesn't have table lookup for it, it can't solve it in one time step. Right? Everybody follow that? Right? You see how first order logic is just really, you play the game and it really, really does help you understand what's going on. Right? Are people following this? Any questions? Can you do this on the test? This is what's going to be on the test. That kind of thing. Right? That's what I want to see on the test. Right? Okay. Let's go on then. I should remember to, I got more slides to put in. I got to put in that. All right. Constant time versus running time. Right? In constant time, so here during compile time, right, when I'm building the machine, then the number of lines of code is fixed. Right? The number of states of the Turing machine is fixed. The range of the variables is fixed. Right? But during runtime, what can grow with the input is how much memory is allocated. Oh, that's funny. Here's the tape alphabet is fixed. Right? The number of cells used. Oh, the instruction set is fixed. This is a weird order in which things are coming in. But anybody ever get this list here? So when we say there exists a machine, what we're saying is you have to decide how many lines of code there are, the range of your variables, your instruction set. You have to decide how many states there are, the transition functions, what you can do in one time step. You have to decide that right there. Right? Does that make sense? And then we say, for all input, now when we know the input, we can just figure out, oh, how much memory are we allocating? What's our runtime? How many cells are used? Right? Does that make sense? Right? This is compile time. And this is runtime. All right. All right, so now we need to convince you, I'm going to do this again. We're going to convince you that Turing machines can do stuff. Right? How can a Turing machine compute? Right? So, well, I can scan the input. Right? You scan the input, and you learn things, and you write what you learn into your states. Right? Just like we were doing. We read in the X, we read in the Y. It's now we store it in our states. That's what's written on Pooh Bear's blackboard. Right? That's the first thing we do is we read the part of the input and we store it in our states. We store what we want to remember. Right? But can we remember the entire input? Right? The adversary says you can't store the entire input, right? Because the input's big. How much of the input can you remember? I don't know how much you can store. You might be able to store 1 billion characters of the input, right? 1 trillion characters of the input. But that's fixed here. At compile time, we decide how many states we're going to have. We decide how much of the characters we're going to remember, right? And then the input's going to grow, right? So you can't remember it's too long. How much can I remember? Some amount, right? But I will remember what I can on my blackboard, right? And once it's on my blackboard, this fixed amount of it, what can I compute about that? Anything, right? Anything in one-time step you can do with table lookup, right? Does that make sense? Right? I compute whatever I want from what I remember, right? Then I can learn, I move ahead and I can learn something else, right? But if I read that into my memory, since my memory is fixed, I have to forget other things, right? You have to erase some of the board to write something else, right? But eventually you have something cool in your memory, right? Once you have something cool in your memory, then you can start writing it on the tape, right? And maybe that's part of the output, or maybe it's a middle calculation, right? You store this middle calculation and you store it somewhere. Now, do you remember where you put it? Well, it's an infinitely long tape, so you might not quite remember where you put it, but you put it somewhere where there's a pattern and you can find it again, right? So then you can come back later and reread it again, right? And so let's not read that. This was a homework assignment, and I translated it into slides. So here's the answer. All right? So this is just to give you